Welcome to Dark Cosmos Theory. Deep within the architecture of reality, there exists a threshold where the fundamental rules governing our universe begin to fracture and dissolve. This barrier manifests at approximately 1.616 times 10 to the negative 35th meters, a measurement we refer to as the Planck length. Past this boundary, our most elegant mathematical frameworks start to stumble into silence. The smooth continuum of spacetime transforms into something that resembles quantum static rather than the seamless tapestry we've come to understand. This evening, we embark on a meticulous examination of this ultimate frontier. We'll investigate what the concept of distance truly represents when our measuring instruments lose all meaning. We'll examine why concentrating enormous amounts of energy into microscopic volumes inevitably triggers gravitational collapse. And we'll uncover how everything from atomic structures to light waves to the cosmos itself seems to encode the same fundamental restrictions into its very fabric. Find a position of comfort. Let your respiratory rhythm settle into a natural cadence, and permit your consciousness to sharpen while your physical body releases tension as we commence this meditative journey into the deepest mysteries of existence. If this exploration provides you with moments of intellectual peace and wonder, a simple gesture of appreciation would mean everything. The act of tapping that like button or pressing subscribe transcends mere digital interaction. It creates a connection through the electronic emptiness, confirming that thoughtful minds continue to congregate in this space to contemplate the profound questions. Every small contribution sustains this sanctuary of curiosity amid the vastness of the internet. Your presence here brings me authentic gratitude. Now, let us begin our investigation with a fundamental question. What precisely fails when we push our observations toward increasingly minute scales? Imagine possessing the capability to magnify inward without constraint, journeying through atomic architectures, penetrating deeper than protons, venturing even more diminutive than the smallest quarks that science has identified. Would the universe persist in revealing successive layers eternally? Or would reality eventually dissolve into incomprehensible chaos, or perhaps absolute nothingness? This isn't idle philosophical musing. It constitutes a legitimate challenge that physicists have grappled with for more than a century, throughout human history. Whenever we've engineered more sophisticated instruments for examining the microscopic domain, from those primitive glass magnifying lenses to the contemporary particle accelerators that span miles, we've consistently adhered to one unbreakable principle. Observing smaller structures necessitates deploying higher energy levels. That represents the core mechanism underlying all microscopic investigation. Electromagnetic radiation, like every wave-based phenomenon in nature, possesses an inherent limitation. It can only resolve objects that exceed its own wavelength in size. The visible light spectrum that human eyes perceive, that familiar rainbow extending from crimson red through violet, carries wavelengths measuring several hundred nanometers. This dimension exceeds a typical atom's diameter by approximately 1,000 times. As a consequence, even our most advanced optical microscopes prove incapable of revealing individual atomic structures directly. The wavelengths are simply too large, washing over atoms like ocean waves passing over pebbles. Shattering through that barrier required scientists to abandon photons and employ electrons instead. Electrons, despite being particles of matter, also demonstrate wave-like properties according to quantum mechanics. Their associated wavelengths can be compressed to far shorter dimensions through acceleration to tremendous velocities. In 1931, the German physicist Ernst Ruska assembled the first functional electron microscope, demonstrating humanity's ability to peer far beyond the limitations imposed by visible light. By carefully manipulating the energy levels of electron beams, he could reduce their effective wavelengths sufficiently to expose cellular organization, crystalline structures, and even individual molecular architectures. The invisible world suddenly became visible through the wave nature of matter itself. 3 decades later, at the Stanford Linear Accelerator Center in California, scientists drove this concept toward what seemed like its ultimate expression. They accelerated electrons to energies reaching tens of billions of electron volts and directed these high-energy beams at protons. The resulting scattering patterns that emerged from those collisions revealed something truly extraordinary. Protons weren't solid, uniform spheres as previously assumed. They contained distinct, smaller concentrations within them, point-like, objects that deflected the electron beams in specific patterns. These became the first experimental confirmation of quarks, the hypothetical particles that had been proposed just a few years earlier by theoretical physicists Murray Gell-Mann and George Zweig. This experiment, designated as deep inelastic scattering, ranks among the most pivotal discoveries in modern particle physics. It demonstrated beyond doubt that matter itself concealed yet another hidden layer of organization. From that watershed moment onward, physicists understood nature's fundamental rule with crystal clarity. Probing smaller distances absolutely requires employing higher energies. There's no way around it. Want to examine the interior structure of an atom? You'll need energies measuring hundreds of electron volts. Desire to investigate inside the nucleus itself? Billions become necessary. Wish to observe what exists at scales smaller than quarks? The required energy ascends to nearly incomprehensible magnitudes. But here's where the fundamental paradox emerges with full force. As we concentrate progressively vaster quantities of energy into increasingly tiny regions of space, we begin distorting the very stage upon which we're attempting to conduct our observations. Space-time itself begins warping under the gravitational influence of that concentrated energy. Einstein's revolutionary insight revealed to us that energy and mass represent merely two different manifestations of the same underlying currency. Compressing excessive energy into microscopic spaces generates gravitational fields so intense that space-time curves dramatically around them. At first, this curvature remains gentle, practically imperceptible to any measurement, but continue elevating those energy levels. Keep attempting to zoom inward, to see finer details, and something genuinely remarkable transpires. The energy you've so carefully concentrated becomes so extraordinarily dense that it collapses under its own gravitational weight. The region you're desperately trying to observe vanishes behind an impenetrable barrier, an event horizon. Your microscope has effectively generated a miniature black hole at the exact point you were trying to examine. That represents the precise moment when the universe extinguishes the light of observation. Beyond this threshold, no instrument conceivable can probe any deeper, because nothing, not even light itself, can escape the gravitational well you've inadvertently created through the act of observation. Physicists have calculated this critical boundary with remarkable precision. We call it the Planck length, approximately 1.616 times 10 to the negative 35th meters. This number utterly defies human comprehension through its sheer minuteness. For perspective, consider this thought experiment. Imagine somehow enlarging a single proton until it matched the entire Earth in diameter. Even at that absurd magnification, the Planck length would still remain, smaller than an individual atom sitting on the surface of that planet-sized proton. At this scale, the familiar concepts of space and time completely abandon any pretense of smoothness. They ripple, fluctuate, and foam like a violently boiling liquid, a phenomenon physicist John Wheeler poetically named quantum foam. Within this seething foam, the universe's geometric structure continuously twists, stretches, and collapses back upon itself. Our comfortable, everyday concepts of distance and duration simply stop carrying any meaningful significance whatsoever. Actually reaching this scale experimentally would demand energies approaching 10 to the 19th power giga-electron volts, a magnitude approximately 15 orders of magnitude beyond what even the Large Hadron Collider can achieve at its maximum capacity. Even if we somehow constructed a particle accelerator that spanned our entire Milky Way galaxy, it still wouldn't suffice to reach these energies. Nature appears to have erected a fundamental protective barrier around her deepest, most intimate secrets. This represents far more than merely a technological constraint or engineering limitation. It's fundamentally physical, woven into the fabric of reality itself. The Planck length functions as a universal boundary, representing the smallest measurement unit that possesses any meaning whatsoever in our universe. Below that threshold, the very conceptual frameworks of space and time lose all definition entirely. It marks the ultimate frontier where quantum mechanics and general relativity clash violently, where some future unified theory of quantum gravity must eventually emerge to reconcile these two pillars of modern physics. NASA's James Webb Space Telescope, the most powerful observatory ever deployed, enables us to gaze backward through cosmic time, observing galaxies as they existed more than 13 billion years ago, mere hundreds of millions of years after the Big Bang itself. But when we direct our investigative attention inward into the fundamental structure of matter rather than outward into space, we're also journeying through time, just in the opposite direction. Each successive layer we uncover through high-energy physics brings us progressively nearer to the extreme conditions and physics that govern the universe's earliest moments. At nuclear energy scales, we encounter echoes, reverberating from the first seconds following the Big Bang. At quark energy levels, we touch the physics characteristic of the initial microseconds of cosmic history. And at the Planck length, we confront the very instant when space-time itself first crystallized into existence from whatever preceded it. So what actually occurs when we attempt zooming beyond that ultimate boundary? Does space dissolve into pure quantum chaos? Or does it unveil an even deeper layer of organization, one that our current theoretical frameworks cannot yet adequately describe? Physicists from Einstein through Hawking and beyond have dedicated their entire professional lives to wrestling with precisely that question. As John Wheeler once eloquently stated, at the Planck scale, space-time's smooth fabric surrenders entirely to a quantum foam of subatomic turbulence and uncertainty. For now, we cannot reach it through any experimental means, but the Planck length stands simultaneously as both an impenetrable barrier and a tantalizing gateway. It represents the boundary of everything we currently comprehend, while also serving as a suggestion, a hint that something far greater and stranger awaits beyond. And so, when we try zooming to infinity, when we push observation to its absolute limits, the universe doesn't provide straightforward answers. Instead, it offers profound silence, a horizon drawn and enforced by its own fundamental laws we're only beginning to understand. But if electromagnetic radiation itself cannot reveal to us nature's smallest truths, perhaps something else, something different, can penetrate deeper. Our next investigation examines precisely why light fails so completely to reveal atomic structures, while electron beams succeed perfectly in this task. If electromagnetic radiation serves as our primary, most fundamental means of perceiving the world around us, why does it fail so spectacularly when we attempt observing matter's fundamental building blocks? Why can't photons reveal atomic structures directly, while electron beams navigate this challenge with apparent ease? Initially, this observation sounds paradoxical, perhaps even contradictory. We conceptualize light as truth's ultimate messenger, the universal carrier of every image we've ever experienced throughout our lives. From the glow of distant galaxies stretching across billions of light years to the soft reflections dancing on water droplets after rain, light delivers the universe to our consciousness. Yet when scientists attempted using light to peer directly into atomic architectures, they discovered essentially nothing but blur and uncertainty. The fundamental problem doesn't originate in our instruments or measurement techniques. It exists within light's intrinsic nature, its fundamental character. Every light ray, every photon, behaves as a wave, and waves possess an absolute, inescapable limitation. They cannot reveal structural details smaller than their own characteristic wavelengths. The visible light that constantly reaches our eyes carries wavelengths around half a micrometer, which equals approximately 500 nanometers. But atoms measure only about 1/10 of a single nanometer across, roughly 5,000 times smaller than visible light wavelengths. So, when we illuminate atoms with visible light, it's directly comparable to attempting to read fine print using swimming pool waves as your illumination source. The ripples simply wash over the details, unable to resolve them, leaving everything blurred beyond recognition. To observe something that incredibly minute, we desperately need significantly shorter waves, something with finer ripples, tighter crests, and troughs that can fit into those tiny spaces. One might reasonably think we should simply employ higher energy light, like X-rays, which possess much shorter wavelengths. And that suggestion is partially correct, representing progress in the right direction. X-rays, with their dramatically compressed wavelengths compared to visible light, can indeed resolve atomic-scale structures with impressive precision. That's precisely why X-ray crystallography became such a revolutionary, transformative tool in structural physics and chemistry. In 1912, Max von Laue directed X-rays at copper sulfate crystals, and the resulting diffraction pattern revealed something profound. Atoms arrange themselves in precise, repeating lattices, ordered structures that X-ray wavelengths could finally resolve. It birthed the entire field of structural physics, opening windows into matter's hidden architecture. But there's a significant complication that limits X-ray imaging. When photons reach energy levels sufficient to match atomic scales, they no longer simply observe atoms passively. They begin actively destroying them, disrupting their structure. A photon energetic enough to match an atom's characteristic scale carries over 10,000 electron volts of energy, sufficient to ionize atoms by ejecting electrons, breaking molecular bonds, and potentially altering or destroying the very crystal structure you're attempting to observe. It's an observer effect taken to the extreme. The act of looking changes what you're looking at so dramatically that the original structure may be lost. That's where electrons enter the picture as our salvation, not as light particles, but as matter particles behaving like waves according to quantum mechanics. In the 1920 seconds, French physicist Louis de Broglie made a simple yet profoundly revolutionary proposal. Every moving particle, he suggested, possesses an associated wavelength just as light does. The faster particles move, the shorter their wavelengths become, inversely proportional to their momentum. He called this the matter wave, the wave-particle duality that lies at the heart of quantum mechanics. 2 years later, this strange, counterintuitive idea found direct experimental verification. In 1927, at Bell Laboratories in New Jersey, physicists Clinton Davison and Lester Germer fired electron beams at nickel crystals and observed clear diffraction patterns. These patterns, characterized by alternating bright and dark bands, can only be generated by waves interfering with themselves. It was as if electrons had temporarily transformed into light, rippling across the crystal's atomic grid like water waves across a pond, creating interference patterns that revealed their wave nature. This single, elegant experiment revolutionized everything we thought we knew about matter. It demonstrated conclusively that an electron beam carrying merely a few hundred electron volts of energy possesses wavelengths small enough to distinguish individual atoms without vaporizing them in the process. That fundamental discovery explains precisely why electron microscopes rapidly replaced optical ones for studying matter's smallest details. In 1931, Ernst Ruska built the first practical electron microscope prototype in Berlin, Germany. His ingenious design employed powerful magnetic lenses to bend and focus electron streams with exquisite precision, generating magnified images of the microscopic world that optical microscopes could never achieve. Within just a few short years of continued development, he could clearly observe viruses, cell membranes, and molecular structures that remained completely invisible to light-based microscopy. There's something genuinely poetic, almost philosophical, about how this unfolded. Light, which illuminates the entire cosmos and enables us to see distant galaxies billions of light-years away, remains fundamentally blind to individual atoms. Meanwhile, electrons, the very substance composing matter itself, can reveal their own hidden geometry with remarkable clarity. The reason lies entirely in the mathematical relationship between energy and wavelength. To make light waves small enough to match an atom's size, you need photons carrying energies around 12,000 electron volts, roughly 1,000 times greater than visible light photons. But electrons moving with only a few hundred electron volts naturally possess wavelengths of comparable magnitude to atomic dimensions. So for identical resolution capabilities, electrons need far less energy than photons and therefore inflict far less damage on delicate specimens. When you compare them directly, the difference feels almost unfair, as if nature deliberately designed electrons for atomic observation. A photon must fight harder, burn hotter with more energy, and risk destroying what it touches just to reveal what an electron can show with relative ease and gentleness. Light, for all its glory in illuminating the macroscopic universe, proves too coarse an instrument for the atomic realm. That's precisely why in contemporary laboratories worldwide, when scientists want to map individual atoms on surfaces or visualize molecular structures with atomic precision, they don't use light at all. They employ finely tuned electron streams, guided by electromagnetic fields, scanned across samples at nanometer precision with extraordinary control. The resulting images aren't constructed from reflected light in the traditional sense, but rather assembled from the complex interactions of matter waves scattering and interfering, painting pictures through quantum probability distributions. Modern transmission electron microscopes achieve resolutions reaching fractions of an angstrom, less than 1/10 of a single nanometer. That's small enough to distinguish individual atomic columns within crystals, to see the arrangement of atoms in materials with stunning clarity. The smallest details we've ever resolved directly approach the scale of a single hydrogen atom's diameter, about 1 angstrom. And it all returns fundamentally to one principle, one inescapable rule. Smaller wavelengths enable finer detail in observation. But while we can keep shortening wavelengths through increasing energy, we can't continue this process forever without consequence. Because, as wavelengths shrink progressively smaller, each probe's energy correspondingly increases. And as we learned earlier, beyond a certain critical point, that concentrated energy begins bending spacetime itself under its own gravitational influence. If you keep trying to look closer and closer, your active observation eventually collapses into gravity, creating the very barrier it cannot penetrate. So the electron microscope represents a kind of optimal middle ground, a careful balance between energy and delicacy, between resolution and preservation. It's powerful enough to reveal atomic structures with exquisite detail, yet gentle enough not to tear those structures apart in the process of observation. It stands as a quiet triumph of human ingenuity and understanding, proving conclusively that we don't always need brute force approaches to see deeper into nature's architecture. Sometimes, elegance and understanding of quantum principles work far better. NASA's own imaging technologies across its mission portfolio rely on remarkably similar principles, just applied at different scales. The James Webb Space Telescope, for example, observes primarily in infrared, employing longer wavelengths than visible light, but it isn't trying to see smaller things. Rather, it's optimized to detect fainter objects, cooler objects, and objects whose light has been redshifted by cosmic expansion. Meanwhile, particle physicists working on Earth use progressively shorter and shorter wavelengths, higher and higher energies, to peer ever deeper into the subatomic world's fabric. Between these two extremes lies a delicate continuum of vision, a spectrum of observation stretching from infinite galactic vastness to the infinitesimal world of atoms and beyond. And within this continuum, light and electrons play distinctly different yet complementary roles. Light tells us how the universe looks from outside, revealing its shapes, colors, motion, and large-scale structure. Electrons tell us how matter is constructed from within, exposing the hidden architecture, the internal scaffolding that supports all material existence. Each approach has its natural limit, each its optimal domain of application. It's worth remembering just how profoundly counterintuitive this discovery was when first made. When Davison and Germer first observed that diffraction pattern back in 1927, they initially didn't believe their own results. Electrons were supposed to be particles, tiny bullets of electric charge, not waves of probability spreading through space. But the pattern was absolutely undeniable, completely unambiguous. It looked exactly like light's characteristic interference fringes, the signature of wave behavior. And suddenly, the rigid boundary between seeing and being, between observer and observed, began to blur into quantum uncertainty. Richard Feynman, one of the greatest physicists of the 20th century, later called this wave-particle duality the central mystery of quantum mechanics. He stated plainly that nature isn't classical in any fundamental sense, and if you want to make a simulation of nature, you'd better make it quantum mechanical from the ground up. That represents the strange beauty underlying this entire story. When we tried using light to see matter at its deepest level, matter itself turned out to possess a kind of light of its own, a wave nature with its own characteristic frequency, its own pattern, its own rhythm. And through that profound realization, we gained the ability to see what ordinary light never could reveal. So why can electrons see atoms while light cannot? Because nature permits matter to reveal itself only through its own intrinsic rhythm, through matter waves born of motion rather than electromagnetic oscillation. And that rhythm, at the atomic scale, belongs to electrons carrying momentum. But the closer we examine, the more another profound mystery begins to rise from the depths. If atoms themselves possess internal structure, do their centers, the protons and neutrons forming the nucleus, also hide something even deeper within them? If we could strike a proton with sufficient force, would it shatter into fragments, or would it reveal a hidden skeleton inside, a deeper layer of reality? That was precisely the haunting question confronting physicists in the late 1960s. For several decades, protons and neutrons had been treated as the solid, indivisible heart of every atom, the fundamental bricks of the atomic nucleus. But strange experimental hints began accumulating, subtle anomalies in scattering data that whispered these bricks might not be truly solid at all. Could there exist something even smaller, more fundamental, lurking within them? By that era, the periodic table had already been comprehensively stripped down to its essential components. Atoms, scientists understood, were mostly empty space, just a tiny nucleus surrounded by a diffuse electron cloud. Ernest Rutherford had proved this conclusively in 1911 through his famous gold foil experiment, firing alpha particles at thin gold foil and observing that most passed straight through undeflected. Only a tiny fraction bounced back, revealing that almost all of an atom's mass was concentrated in a nucleus, measuring just 100,000th of the atom's diameter. It was almost incredible, Rutherford famously remarked, as if you fired a 15-inch artillery shell at tissue paper and it came back to strike you. But now, more than half a century later, in the 1960 seconds, scientists wanted to penetrate deeper still, to ask whether even that incredibly dense nucleus was truly solid and fundamental, or whether it too concealed an inner world, hidden layers within layers. To find out, they would need to strike the nucleus with something far more precise than alpha particles, and with energies far greater than anything ever attempted before in the history of physics. The place that made this ambitious investigation possible was the Stanford Linear Accelerator Center, universally known by its acronym SLAC, located in California. Completed in 1966, it represented a true marvel of its time, perhaps the most ambitious scientific instrument ever constructed. A perfectly straight, 2-mile-long tunnel burrowed through the Earth, specifically designed to accelerate electrons to velocities approaching the speed of light itself. By early 1962 standards, it was a machine of seemingly impossible ambition, a tool capable of probing matter's deepest, most fundamental layers ever made accessible to humanity's curiosity. Electrons were chosen for this experiment for very specific reasons. They are apparently point-like particles with no known internal structure, no compositeness, and when they scatter elastically off targets, they reveal with extraordinary precision the shape and structure of whatever lies inside that target. In essence, each high-speed electron functions as a tiny radar pulse of the subatomic world, an ultrafine probe that lets physicists map structures that cannot be seen through any form of microscopy. So the core idea was elegantly simple, but scientifically radical. Fire electron beams, carrying energies of tens of billions of electron volts at protons and neutrons residing inside atomic nuclei, and carefully observe how they scatter. If the nucleus were truly solid and structureless, electrons would scatter in smooth, predictable patterns. But if the nucleus contained smaller constituent pieces, within it, electrons would bounce off in complex, irregular patterns that would betray the hidden internal structure. That was the fundamental logic behind what would become one of the most famous and consequential experiments in modern physics, designated deep inelastic scattering. Inelastic because the collisions weren't gentle, glancing blows that left everything intact. The electrons struck so violently hard that they transferred significant energy into the protons, shaking them apart, disrupting their structure in ways that revealed their internal composition. When the experimental data first came streaming in around 1968, it absolutely didn't fit expectations for a solid, uniform sphere at all. Electrons didn't bounce as if the proton were a single, featureless lump of matter. Instead, they scattered in sharp, point-like bursts of specific angles, as if the electron beam were ricocheting off smaller, harder targets hidden inside, like marbles inside a balloon. Those characteristic scattering patterns told a story that no one could ignore or dismiss. Inside every proton, there seemed to exist 3 smaller concentrations of electric charge, 3 distinct points of resistance that deflected electrons most strongly at particular angles. These scattering results became the first direct experimental evidence for quarks, the hypothetical particles that had been proposed just a few years earlier by theoretical physicists Murray Gell-Mann and George Zweig. Gell-Mann had coined the whimsical term quark back in 1964, borrowing it from a cryptic line in James Joyce's experimental novel Finnegan's Wake, 3 quarks for Muster Mark. It was an intentionally playful name for what was, at that time, a purely mathematical concept with no experimental confirmation. No one had actually observed a quark directly. They had been introduced primarily to explain the bewildering proliferation of particles emerging from earlier particle physics experiments, a zoo of hadrons that seemed to have no organizing principle. But now, the SLAC experimental data made that abstract mathematical idea physically real, grounding it in observation. The conclusion was genuinely stunning to the physics community. Protons and neutrons, once confidently thought to be the final solid units of matter, the ultimate building blocks, were in fact composite structures themselves. Each was made of 3 quarks bound together extraordinarily tightly by powerful forces that physicists were only beginning to understand. These forces would later be comprehensively described by a new quantum field theory called quantum chromodynamics, universally abbreviated as QCD. This became the accepted theory of the strong nuclear force, one of the 4 fundamental forces of nature. The strong force, physicists discovered, behaves unlike any other force in nature. It possesses the bizarre property of growing stronger as you attempt to pull quarks farther apart rather than weakening, with distance like gravity or electromagnetism. It's comparable to a rubber band that stretches with increasing tension but never actually breaks no matter how hard you pull. The energy required to completely separate quarks becomes so extraordinarily great that it spontaneously creates entirely new quark-antiquark pairs from the vacuum before the original quarks can be freed and isolated. That's the fundamental reason why no physicist has ever successfully isolated a single free quark in any experiment. They remain forever confined within composite particles called hadrons, which include protons, neutrons, and many other particles composed of either three quarks or quark-antiquark pairs. This discovery completely revolutionized our understanding of matter at its most fundamental level. The nucleus, far from being solid in any conventional sense, is mostly space threaded through with extremely energetic quantum fields. Quarks dance inside a dense, roiling cloud of gluons, the force-carrying particles of the strong force. These gluons continually appear and vanish, exchanging energy at speeds approaching light itself. If we could somehow look directly inside a single proton with sufficient resolution, it wouldn't look like a hard sphere at all. Instead, it would appear vibrantly alive, a flickering storm of quantum motion, a churning sea of virtual particles colliding and dissolving billions upon billions of times per second. Subsequent experiments, since those pioneering SLAC investigations, have refined this picture with extraordinary, almost unbelievable detail. At CERN in Europe and Fermilab in America, increasingly powerful particle accelerators have smashed protons together at progressively higher energies, confirming repeatedly that quarks behave as nearly free particles when struck at very short distances, a remarkable property physicists call asymptotic freedom. But as their separation grows even slightly, the strong force tightens its grip again, inexorably drawing them back into permanent confinement within hadrons. This unique behavior is absolutely unprecedented in physics. Most forces we encounter, like gravity or electromagnetism, grow steadily weaker as objects move farther apart. The strong force does precisely the opposite, defying our everyday intuitions. It ensures categorically that quarks can never escape the quantum prison of their own creation. And yet, paradoxically, this extreme confinement is precisely the reason matter remains stable across cosmic timescales. The tremendous strength of the strong force holds protons together essentially forever, for timescales vastly longer than the current age of the universe itself. It constitutes the fundamental reason atoms can exist at all, the underlying reason stars can burn steadily for billions of years, and ultimately the reason you, listening to this right now, are still here as a stable configuration of matter, the characteristic energy scale needed to probe such infinitesimal depths, around 1 billion electron volts or 1 GeV, corresponds to distances of approximately 1/4 of a meter or 1 femtometer. At that almost incomprehensible level, the familiar distinction between solid matter and empty space begins to blur into quantum ambiguity. Matter, it increasingly seems, consists mostly of absolute nothingness, except for the quantum fields and binding energy that somehow organize nothing into something tangible and stable. Even today, decades later, SLAC's scientific legacy remains one of the most elegant examples in physics of how we learn fundamental truths by scattering particles off each other. We throw particles at particles with enormous energy and carefully read the universe in the subtle ways they recoil, in the angles and energies of their deflection. It's directly analogous to striking a bell suspended in complete darkness and listening attentively to its echoes and resonances to deduce what material it's made of, its shape, its internal structure. And yet, even the quark layer might not represent the absolutely final, most fundamental layer of reality. Some physicists harbor suspicions that there could exist even smaller entities, hypothetical preons, hidden beneath quarks themselves, though absolutely no experimental evidence yet confirms or even suggests this. The search for ever deeper layers continues relentlessly, but each step deeper demands energies far, far beyond our current technological reach. As the legendary physicist Richard Feynman once eloquently said about the SLAC results, we discovered that the world is vastly more complex and more interesting than anyone had dared imagine. That profound statement still holds completely true today. Every single time we successfully peel back one layer of nature's organization, we invariably find a deeper mystery waiting patiently beneath. And as our particle accelerators grow progressively more powerful, so do the fundamental questions they force us to confront. If we keep raising collision energies, keep smashing protons together harder and harder, will we eventually reach some ultimate limit where even the strong force itself gives way to something entirely new and unexpected? That represents the next frontier of discovery. When our instruments reach collision energies measured in trillions of electron volts, do we simply observe more of the same quarks and gluons, or will something stranger still emerge from the quantum vacuum? What actually happens when you construct a machine so extraordinarily powerful it can temporarily tear open the vacuum itself, creating conditions that haven't existed since the first microseconds after the Big Bang? Can such a machine really reveal reality's hidden layers directly, or does it merely disturb them for a fleeting instant before they vanish again into quantum uncertainty? That's the fundamental question behind the Large Hadron Collider, universally known as the LHC, the most ambitious scientific instrument ever constructed by human civilization. Many people imagine it as some kind of weapon, or perhaps as a ring of unimaginable destructive energy buried beneath the border between France and Switzerland. But in truth, the LHC functions as a kind of microscope, an absolutely gigantic yet precise eye that doesn't use glass lenses or light, but instead employs powerful magnetic fields and protons, moving at 99.999999% of light speed. Its goal appears simple in concept, but proves almost impossibly difficult in execution. To look deeper into matter's structure than any human eye has ever penetrated, the LHC accelerates two proton beams in opposite directions around a perfectly circular tunnel, measuring 27 kilometers in circumference, buried about 100 meters underground. Each beam carries particles energized to approximately 7 trillion electron volts, abbreviated as 7 TeV. When these beams collide head-on at designated interaction points, the total center of mass energy of each crash reaches 14 TeV. That enormous number wasn't chosen randomly or arbitrarily. It was carefully selected because it sits near a crucial theoretical threshold, an energy scale where the Higgs field, the invisible quantum field permeating all space that gives mass to fundamental particles, can be shaken violently enough to produce a detectable ripple. That ripple manifests as the Higgs boson, an extremely short-lived particle that proved the Higgs field's existence. This is precisely what physicists mean when they say the LHC can see or detect the Higgs boson. The instrument isn't looking at the field directly, which is impossible. Instead, it's striking the Higgs field like hitting the surface of a perfectly still pond with tremendous force to reveal a single fleeting wave, a quantum excitation that briefly materializes before dissolving. When those two proton beams collide at interaction points inside massive detectors, their combined energy compresses into a point far smaller than an atom's nucleus, briefly recreating extreme conditions that last existed less than 1/trillionth of a second after the Big Bang itself. For an infinitesimally brief moment, the vacuum of space itself behaves entirely differently than normal. Virtual particles appear and disappear in quantum fluctuations. Energy spontaneously converts into mass, and mass back into energy. The same fundamental processes that once shaped the newborn universe replay on microscopic scales. But to properly understand why the LHC truly is a microscope rather than just a collider or particle destroyer, we need to remember one fundamental rule that connects all scales of observation. The higher the collision energy, the smaller the distance you can effectively probe. This represents the guiding principle of all modern high-energy physics. Every increase in energy sharpens our vision of the microscopic world, like turning a focusing knob on a microscope. When we used ordinary visible light, we could see cellular structures. When we employed electron beams, we saw individual atoms. When we used billion electron-volt beams at SLAC, we finally saw quarks. And now, with trillion electron-volt level energies at the LHC, we can directly disturb the very quantum fields that make those quarks possible, the fundamental fields underlying all of reality. Inside the LHC tunnel, each proton beam is guided with extraordinary precision by 1,232 superconducting dipole magnets, cooled to approximately 1.9 Kelvin using liquid helium, colder than the temperature of outer space itself. The vacuum inside the beam pipe is maintained emptier than the void between stars, containing fewer particles per cubic meter than interstellar space. Every component, every magnetic pulse, every precisely timed adjustment is designed with one goal: to keep those two beams aligned to within a tiny fraction of a millimeter over their entire 27-kilometer journey. When they finally collide at designated interaction points, they do so inside detectors the size of multi-story buildings: ATLAS, CMS, ALICE, and LHCb. These enormous, extraordinarily complex instruments were built not to destroy particles, but to listen, to observe with exquisite sensitivity. ATLAS and CMS, the twin giants of the LHC detector array, are what allowed physicists to detect and confirm the Higgs boson back in 2012, one of the most significant discoveries in physics history. Each individual collision event is recorded by millions of individual sensors positioned throughout these cathedral-sized detectors. Out of more than 1 billion collisions occurring every single second, only a few exceptionally rare ones produce the characteristic decay patterns that definitively signify a Higgs boson was created. And even those telltale traces exist for less than 1/trillionth of a second before dissolving into cascades of other particles that the detectors can actually observe. When the Higgs boson discovery was finally confirmed with sufficient statistical significance, Peter Higgs himself, then in his 80s, said softly with evident emotion, "It's really an incredible thing that it has all come true after so many decades. It wasn't just another discovery to be catalogued. It represented proof that the standard model of particle physics, the theoretical framework describing all known particles and forces except gravity, was complete in one profound sense. The final missing piece of that elaborate puzzle had been found, but the deeper, more fundamental question still remains unanswered. How deep can the LHC really probe? How fine is its effective resolution? If we treat it as a cosmic microscope, examining matter's deepest structure at its maximum energy of 14 TeV, the LHC can probe distances down to approximately 1/100th of a femtometer, which equals 10 to the -18th meters. That's dramatically smaller than a proton's radius, approaching the 9 fundamental scale, where quarks and gluons swirl in their permanent quantum confinement. At this almost unimaginable level, we're not just observing particles anymore in any conventional sense. We're directly exploring quantum fields themselves, continuous backgrounds that permeate every cubic centimeter of space. The Higgs field that gives particles mass, the electromagnetic field that mediates light and electric forces, the strong and weak nuclear fields. These aren't discrete things that exist inside space as we normally think of it. They are space itself in constant quantum motion. Each violent collision at the LHC momentarily shakes those fields with tremendous energy, revealing how they interact with each other, how they couple, how they exchange energy and momentum. Yet for all its tremendous power and sophistication, the LHC remains very far from possessing the energy needed to directly observe the Planck scale, the ultimate limit we discussed at the beginning. To reach that inconceivable threshold, we would need to boost protons not to 7 TeV, but to approximately 10 billion trillion TeV, requiring a particle accelerator the size of our entire galaxy. So the LHC clearly is not the final, ultimate microscope humanity will ever build. Instead, it functions as a crucial bridge, the sharpest observational tool we currently possess between the known and the unknown realms of physics. Its discoveries reach far beyond particle physics into the very structure of our understanding of reality. Because when you push collision energies high enough, something remarkable happens. You don't just see smaller pre-existing things in greater detail. You actually create entirely new particles and phenomena from pure energy through Einstein's mass-energy equivalence. That's what makes the LHC so qualitatively different from any microscope that came before it in history. It doesn't only passively observe the world as it naturally exists. It briefly recreates pieces of the early universe, particle by particle, collision by collision, from pure, concentrated energy. The massive detectors record these fleeting moments with truly astonishing precision. Each proton-proton collision releases jets of particles streaming in all directions, photons, neutrinos, and various exotic particles. Sophisticated computer algorithms then trace those fragments backward in time, reconstructing what happened at the precise instant of impact with extraordinary detail. It's as if you dropped a watch onto a hard floor, heard hundreds of tiny pieces scatter in all directions, and then deduced the watch's complete internal structure and mechanism from the sounds alone, from the patterns of scattering. The sheer volume of data produced is so staggeringly immense that it requires computing systems distributed across the entire world. The worldwide LHC computing grid connects hundreds of research institutions in over 40 countries. Each single second of collision operation produces more raw data than an entire human lifetime of internet traffic. Every single bit of that information must be carefully filtered, thoroughly analyzed, and systematically compared against the detailed predictions of theoretical models. This represents one of the most remarkable collaborations in human history, cooperation at planetary scale to understand the tiniest, most fundamental pieces of existence. There's something quietly moving about that achievement. Not poetic exactly, but profound in its precision and scope. In the years since the historic Higgs discovery, the LHC has ventured far beyond that single triumph. It has systematically searched for supersymmetric partner particles, hypothetical heavier cousins of known particles predicted by certain extensions beyond the standard model. None have yet been found within the energy ranges explored. It has examined extraordinarily rare particle decay processes, hunted persistently for any hints of dark matter particles, and measured the strong force between quarks at unprecedented energies with remarkable precision. Every operational run brings instrumental refinements, technical upgrades, and higher luminosity, meaning more collisions per second, sharper data, deeper insight into nature's workings. The upcoming high luminosity upgrade of the LHC will multiply its discovery reach even further, revealing whether nature hides surprises at energy scales we haven't yet fully explored. But beyond all the technical mastery and engineering achievements, there's a profound question that lingers in every control room at CERN, in every late-night analysis session. If we've now conclusively seen the Higgs boson successfully completing the standard model, what fundamental discoveries come next? If the standard model is mathematically complete as it appears, why does the universe still feel profoundly unfinished, with dark matter comprising 85% of matter, dark energy accelerating cosmic expansion, and gravity itself still standing completely apart from quantum theory? Maybe the answer to these mysteries lies just barely beyond the reach of 14 TeV collisions. Maybe we need to push to hundreds or thousands of TeV to see the next threshold, the next hidden layer of physical reality. Or perhaps the crucial clues are already present somewhere in the existing mountains of data, patiently waiting to be noticed by someone asking exactly the right question in exactly the right way. As CERN physicist Fabiola Gianotti said thoughtfully after the Higgs discovery was announced, "We have reached a milestone, but it is a new beginning, not an ending." And indeed, that's what the LHC truly represents. Not a final answer or conclusion, but a doorway opening. The sharpest eye humanity has yet built, one that looks not through glass or lenses, but through pure energy itself. a machine that lets us watch the universe replay its opening act, one collision at a time, teaching us what matter truly is at its deepest level. But what happens when even this enormous energy begins to push against an even deeper law of nature? When our determined effort to see more and more causes gravity itself to push back with overwhelming force? What if the closer we attempt to look into the universe's structure, the more forcefully the universe pushes back against our observation? What if instead of revealing progressively finer details as we expect, nature itself begins to collapse under the weight of our curiosity? This isn't science fiction or imagination. It represents the quiet revenge of gravity, a fundamental limit built directly into space-time's structure itself. At first glance, it sounds almost paradoxical. How could simply looking too closely, simply observing with too much energy, possibly create a black hole? But that's exactly what inevitably happens when observation energy becomes too intense, too concentrated in space. Let's begin by examining this carefully. Every attempt to observe smaller structures necessarily requires more energy, as we've established. To probe inside atoms, we need electron beams accelerated to hundreds of electron volts. To peer inside the nucleus, we require energies of millions or billions of electron volts. The rule is absolutely simple and inescapable. Finer details demand shorter wavelengths, and shorter wavelengths invariably come from higher energy particles. But here's where the universe turns that rule against us with inexorable logic. The more energy we focus into a small region of space, the more that energy itself curves space-time through its gravitational influence. Einstein's general relativity tells us explicitly that energy, just like mass, creates gravity and warps space-time. So every time we push our microscope to higher power, to finer resolution, we also strengthen the gravitational field inside the tiny region we're attempting to observe. At first, this effect is utterly tiny, completely negligible for any practical purpose. But as we push beyond atomic scales, beyond nuclear scales, into the realms of quarks and gluons, and beyond, energy density grows to truly unimaginable levels. Eventually, inevitably, a strange critical balance emerges. The energy we're using to probe a region becomes so extraordinarily concentrated that the gravity it creates actually traps light itself within that region. The region we're trying to observe forms its own event horizon, becoming a miniature black hole. That's gravity's counterattack, the moment when looking too closely makes everything vanish behind an impenetrable curtain. Physicists can describe this phenomenon in straightforward terms using established physics. If you compress enough energy into a sufficiently small space, that region behaves gravitationally, as if it has mass, according to Einstein's E equals mc squared. And if the gravity from that effective mass becomes strong enough, it forms a boundary, a critical radius within which light cannot escape. That's the Schwarzschild radius, the size of the event horizon. When the size of the region you're trying to examine shrinks down to the same scale as this Schwarzschild radius, the observation game is fundamentally over. Adding more energy doesn't help you see smaller details or finer structure. It just makes the black hole bigger, expanding the region you cannot observe. This represents the cosmic version of diminishing returns, the ultimate physical limit of observation encoded in nature itself. It tells us there's a smallest meaningful length in nature, approximately 1.616 times 10 to the negative 35 meters, the Planck length we keep returning to. At that fundamental scale, the gravitational radius of the concentrated energy equals the region itself. Any attempt to focus harder, to probe deeper, inevitably collapses the experiment into a black hole. To put this in proper perspective, the protons circulating inside the Large Hadron Collider reach energies of about 7 trillion electron volts, probing distances down to roughly 1/10 of a femtometer. To actually reach the Planck length through direct observation would require energies approximately 1 trillion times greater, about 10 to the 19th power giga electron volts. That's more energy than all the power produced by every single star in the observable universe, all focused into a single quantum of action. So the universe protects its smallest scales behind a gravitational curtain that proves absolutely impenetrable. The closer we attempt to look, the stronger that curtain pulls shut through pure gravitational collapse. This isn't a failure of our technology or ingenuity. It's a fundamental, inescapable property of space-time itself, woven into its very fabric. Physicists sometimes describe this interplay as a duel between quantum mechanics and gravity, two titans of physics locked in eternal struggle. Quantum mechanics constantly encourages us to look closer, to sharpen our measurements indefinitely, to localize energy into smaller and smaller regions. But gravity systematically punishes that ambition with increasing severity. It dictates that the more you concentrate energy, the more space-time curves around it, until eventually the very concept of position itself disappears behind an event horizon. At first, this idea existed as just a theoretical curiosity, an interesting thought experiment. But it has profound, far-reaching consequences for the way we think about the universe and the limits of knowledge. It means there is a boundary not just of what we can build with current technology, but of what can exist and be observed according to the laws of physics themselves. Beyond that limit, physics as we know it simply cannot describe what happens. The equations break down, singularities appear, and our theories lose all predictive power. To get a visceral feeling for how incredibly small this fundamental limit really is, imagine zooming in on a single proton as if looking through a microscope. Now imagine zooming approximately 1 trillion times further inward. You're now at the Planck scale, where familiar distances lose all meaning, where time and space fluctuate wildly like foam on a turbulent sea. At this point, gravity and quantum effects are equally strong and fundamentally inseparable, and neither can be ignored in any calculation. This critical threshold, where energy concentration, gravity, and measurement capability collide catastrophically, is sometimes called the black hole barrier by physicists. No matter what measurement technique we hypothetically use, any attempt to see beyond this barrier triggers immediate gravitational collapse. The act of observation creates the very impenetrable wall it cannot cross. And this isn't merely abstract theory disconnected from reality. Exactly the same logic explains why black holes in space possess event horizons. When a massive star collapses at the end of its life, its mass is compressed into such an incredibly tiny volume that its gravitational Schwarzschild radius exceeds its physical size. Light can no longer escape from within that radius, and the star's core disappears forever behind a horizon, cut off from the external universe. In our case, the same fundamental principle applies not to collapsing stars, but to observation experiments. The energy we concentrate for measurement creates its own horizon. In 1976, the renowned physicist Kip Thorne described this elegantly in a technical paper. The closer you get to the interface of the gravitational radius, the more violently the laws of physics resist your intrusion. That resistance is precisely what defines the Planck scale fundamentally. It's not a wall in any ordinary physical sense. Nothing tangible is blocking the view like a barrier. It's a limit in the very geometry of reality itself. Distances, time intervals, even the conceptual distinction between inside and outside all lose their meaning at that scale. In this sense, gravity's counterattack isn't destructive, but deeply protective. It prevents us from accidentally tearing the universe apart, from creating uncontrollable singularities. It ensures that energy, matter, and space-time remain balanced, that the universe remains stable and comprehensible. And yet, this fundamental limit also leaves us with an unfinished story, an incomplete picture. Because if we can't see what happens beyond that boundary, if observation itself becomes impossible, how can we ever truly know what space-time is made of at its absolute core? Are we forever trapped outside the deepest layer of reality, unable to penetrate the final veil? That profound question is what drives the ongoing search for a complete theory of quantum gravity, a unified framework that would seamlessly unite Einstein's general relativity with quantum mechanics. The hope is that such a theory will describe how space-time behaves when it becomes as small and turbulent as the quantum particles it contains. Some theorists think it might resemble a network of discrete loops, the spin networks of loop quantum gravity. Others imagine vibrating strings, tiny one-dimensional filaments whose oscillations replace the chaos of collapsing points. But until such a theory is complete and tested, we must live with this profound paradox. The smaller we look, the more gravity bends our window shut. The harder we try to see the foundations of the universe, the more insistently the universe hides them behind event horizons. Still, this delicate balance between energy and gravity, between curiosity and collapse, is what makes the cosmos stable and long-lived. It's the quiet law that keeps stars from imploding too quickly and keeps atoms from tearing apart spontaneously. It defines not just a limit of knowledge, but the very architecture of stable existence itself. As Stephen Hawking once noted with characteristic insight, the closer you get to a black hole's event horizon, the more time slows down until it stops entirely at the horizon itself. At the Planck scale, perhaps time itself pauses or becomes meaningless, not because we reach the end of space, but because the very act of measurement loses all meaning. And yet, even this gravitational counterattack gives rise to one of the most fascinating frontiers in modern theoretical physics, the place where quantum theory and gravity must finally meet and merge. Because if space-time collapses when we look too closely, what happens when quantum uncertainty is also taken fully into account? Is there truly a smallest possible size in the universe? A fundamental scale beneath which distance itself stops making sense as a concept. Physicists call that frontier the Planck Length, the line where the laws of nature, as we know them, begin to unravel completely. It's not simply a matter of needing smaller rulers or more powerful microscopes. It's a deep question of whether the concept of space itself can even exist meaningfully below a certain scale. To understand why this matters so profoundly, let's trace how this strange number, approximately 1.61, 6 times 10 to the negative 35 meters, was actually born. It didn't come from experiment or direct measurement, but from pure dimensional reasoning. When physicists combined three of nature's fundamental constants, the speed of light, Newton's gravitational constant, and Planck's constant of quantum action, they discovered that these values naturally combine mathematically into a single characteristic unit of length. That number marks the scale where both quantum mechanics and gravity become equally strong, where neither can be neglected. Below it, neither theory can adequately describe what happens. Einstein's smooth spacetime from general relativity and the restless probabilities of quantum theory collide violently, and both fail completely. To visualize how incredibly small this really is, imagine shrinking yourself down step by step through the scales of nature. Human hair is about 1/10 of a millimeter wide, visible to the naked eye. A red blood cell is roughly 1,000 times smaller than that. A typical proton is approximately 10 billion times smaller than a red blood cell. Now keep dividing that proton's diameter by 10 billion again and then again, repeating 30 times in a row. That's the Planck length, unimaginably tiny. At that point, space is no longer a quiet, smooth fabric. It churns and flickers violently, its geometry twisting under quantum uncertainty and gravitational tension simultaneously. The distances between points blur into quantum probability distributions. The very meaning of before and after becomes uncertain. John Wheeler, one of Einstein's last collaborators, called it quantum foam with characteristic insight. In this foam, space-time is not continuous or passive, but dynamic, alive, and fundamentally unstable. Tiny virtual wormholes open and close in trillionths of a second. Energy fluctuates violently in accordance with Heisenberg uncertainty, creating brief bursts of space-time curvature that rise and vanish like bubbles in boiling water. What we confidently think of as empty space at human scales is, at the Planck scale, a churning storm of quantum geometry. The energy required to reach such scales experimentally is beyond any imagination. It's called the Planck energy, roughly 10 to the 19th power giga-electron volts, or about 2 billion joules, concentrated into a single quantum interaction. For comparison, the Large Hadron Collider, the most powerful particle accelerator on Earth, reaches only 14 tera-electron volts, approximately 15 orders of magnitude smaller. To build an accelerator that could actually reach the Planck energy, it would have to be as large as several thousand light-years across, spanning interstellar distances. This isn't impossible just for current technology. It's impossible by the very structure of the universe itself. The moment you tried to create such enormous energies in such small regions, they would instantly collapse gravitationally into black holes. This limit isn't about engineering challenges or funding. It's a limit of fundamental principle, built into the fabric of reality. Because at those energies, the gravitational pull of the energy itself would instantly collapse into a black hole before any measurement could be completed. Nature draws a curtain not of matter or energy, but of meaning itself. Physicists have long debated what this curtain truly represents. Some see it as a wall, a genuine minimum unit of space, like pixels in a cosmic screen. Others see it as a threshold, a smooth transition into an as-yet unknown realm where gravity and quantum theory finally merge into something new. Either way, it's the scale where our mathematics begins to whisper insistently, "You can't go any further with current physics." It's almost poetic in its precision and inevitability. From the Planck length, we can also define the Planck time, the shortest possible moment that can be meaningfully measured, approximately 10 to the negative 44 seconds. Below that infinitesimal duration, the sequence of cause and effect blurs into quantum uncertainty. Time ceases to flow in the way we understand it. These scales mark the earliest possible chapter of cosmic history, the moment just after the Big Bang, before the laws of physics froze into their familiar forms that govern our universe today. NASA's and ESA's missions, from COBE to WMAP to the Planck satellite, have mapped the afterglow of that ancient moment with extraordinary precision. The cosmic microwave background reveals the universe as it was about 380,000 years after the Big Bang, but they can only look back to when the universe was already comparatively old and cool. The true Planck era, by contrast, ended when the universe was less than 1/trillionth of a second old. At that unimaginably early time, everything we know today, matter, energy, even the geometry of space itself, was still tangled together in ways we barely understand. The four fundamental forces had not yet separated into distinct interactions. The Higgs field had not yet condensed to give particles mass. The universe itself was far smaller than a single atom, yet somehow contained the seeds of all future galaxies, stars, and planets. The Planck scale, then, is not just an abstract number. It's the edge of our cosmic memory, the boundary of what we can theoretically understand with current physics. It's where the known laws break down completely and something deeper must begin. To go beyond it, we desperately need new physics, new theories, but attempts to describe what happens there continue. String theory replaces point particles with one-dimensional loops of energy, each about the size of the Planck length. Loop quantum gravity, on the other hand, suggests that space itself is built from discrete units, little quanta of area and volume connected in a vast network. Both theories, despite their profound differences in approach, agree on one profound thing. Below the Planck scale, distance itself ceases to be a measurable quantity in any meaningful sense. You can't say something is half a Planck length apart any more than you can have half of a photon or half of an electron. It's not just too small to measure practically. It's fundamentally undefined by the physics we know. That makes the Planck length not a wall we might someday climb over with better technology, but a horizon we can never cross with any technology. It's a fundamental boundary between what can exist and be observed and what can only be imagined through mathematics. It's the smallest tick on the ruler of reality, the final marking before meaning itself dissolves. Yet there's a quiet irony worth noting. The constant that defines the Planck length, Newton's gravitational constant g, is also the least precisely measured of all fundamental constants in physics. We know the speed of light and Planck's constant with exquisite, almost unbelievable precision. But gravity still eludes our most careful measurements, which means, in a strange way, the most fundamental scale in physics depends on the one constant we understand the least precisely. Still, the idea of a minimal length has profound practical consequences for physics. It means there's an ultimate limit to how much information the universe can store in any given volume of space. According to the holographic principle, developed by Gerard 't Hooft and Leonard Susskind, the total information inside any region is proportional not to its volume but to its surface area, measured in Planck units. In other words, reality might be fundamentally pixelated at the Planck scale, each pixel carrying one bit of quantum information. This idea underlies modern black hole physics entirely. When Stephen Hawking discovered that black holes radiate energy slowly over time, the rate of that radiation turned out to depend directly on the Planck area, the square of the Planck length. It was the first concrete hint that the universe at its deepest level may count information in Planck-sized pieces, in discrete quantum units. So is the Planck length truly the end of reality, or just the beginning of something even deeper? For now, we simply cannot say with certainty. It's the smallest scale we can define mathematically. But whether nature actually quantizes space there, whether space-time really is discrete at that scale, remains one of the most profound open questions in all of science. And it's a humbling thought for humanity. Every measurement, every observation, every law of physics rests fundamentally on the assumption that space and time are continuous, smooth backgrounds. But if they're not continuous, if they're actually built from discrete Planck-sized building blocks like atoms of geometry, then our entire view of the universe is only an approximation, an effective theory valid at large scales. As physicist Carlo Rovelli once eloquently said, at the Planck scale, space is not continuous. It's made of quanta, discrete units. The world is woven from loops of gravity, a cosmic tapestry. It's a quiet but profound reminder that beneath the smoothness we perceive lies a granular, vibrating foundation we cannot directly observe. And if the Planck length is indeed the last wall of the visible, observable world, what lies beyond that wall might not be smaller in any conventional sense, but entirely different in character. Perhaps space and time themselves are just emergent properties of something else, something even more fundamental that we haven't yet conceived, which brings us naturally to the next mystery. If there truly is a minimum distance encoded in nature, does the famous uncertainty principle itself change when gravity fully joins the quantum game? If every photon we use to measure a point in space also bends that space gravitationally, then what does precision to even mean anymore? That is the heart of one of the most delicate puzzles in modern physics. The search for understanding how quantum uncertainty fundamentally changes when gravity enters the equation in a way that cannot be ignored. It all begins with a principle so fundamental that it reshaped all of science in the 20th century, Heisenberg's uncertainty principle. In the 1920 seconds, Werner Heisenberg realized something profound about quantum mechanics. You can never know both the position and momentum of a particle with perfect, arbitrary accuracy simultaneously. The more precisely you pin down exactly where something is, the more uncertain its motion becomes. And the more precisely you measure its momentum, the blurrier its position grows. The universe at its smallest scales refuses to stand still under observation, refuses to be pinned down completely. This is not merely a limit of our instruments or measurement techniques. It's a fundamental property of nature itself, built into quantum mechanics. Even in a perfect laboratory with infinite skill and unlimited resources, the uncertainty would remain. It's as if reality hides its coordinates behind a soft veil of probability, a quantum fuzziness that cannot be eliminated. But Heisenberg's principle, elegant and profound as it is, was written for a world without gravity. It describes the quantum domain, where energy and probability dance, but where spacetime's geometry stays fixed and flat, unaffected by the particles it contains. Once we invite gravity into this picture, once we allow energy itself to bend the stage it plays on, that delicate balance begins to break down in interesting ways. Imagine you're trying to locate an electron with extreme precision using light. You shine a photon at it, a particle of light with a certain wavelength. If you use light with a long wavelength, you can't see details smaller than that wave size due to the wave nature of light, so you choose shorter and shorter wavelengths, higher energy photons, to get a sharper image of the electron's position. But at some point, inevitably, your photon becomes so energetic that its own gravitational influence begins to matter. That single photon now carries enough energy to distort spacetime ever so slightly around the region you're observing. The act of measurement begins to bend the very coordinates you're trying to measure. If you keep pushing relentlessly to higher energies, the distortion grows progressively worse. Eventually, the photon's energy density becomes so extreme that it would create a tiny gravitational well, a miniature black hole forming right where you tried to take your measurement. Instead of seeing more detail as you'd hoped, you lose everything behind an event horizon. This idea leads directly to what physicists call the Generalized Uncertainty Principle, or GUP. It says that Heisenberg's uncertainty rule must be fundamentally modified when gravity becomes strong enough to affect measurements. At low energies, the usual quantum behavior dominates as expected. The more you know a particle's momentum, the less you know its position. But as you increase energy, and therefore increase gravitational influence, something genuinely new happens. The uncertainty in position stops shrinking as you add energy. It reaches a minimum value and then begins to grow again, getting worse rather than better. In other words, there is a smallest measurable distance in the universe, a genuine minimum. A point where trying to look closer actually makes your vision blurrier rather than sharper. That minimum distance matches the Planck length we've discussed, approximately 1.616 times 10 to the negative 35 meters. This result is reached not through cosmology, not through high-energy collider experiments, but by pure reasoning about how measurement, energy, and gravity must interact at extreme scales. The beauty of this idea is that it connects two of the most powerful theories in science without forcing them to merge completely. From the quantum side, Heisenberg gave us a law about fundamental limits of precision. From the gravitational side, Einstein told us that energy bends spacetime. The generalized uncertainty principle is where those two profound truths meet, softly, mathematically, and inevitably. It means that even if we never build a machine powerful enough to reach the Planck energy directly, nature has already built its own safeguard into reality. The fabric of spacetime itself won't allow us to squeeze information into a region smaller than that scale. It's physically impossible. This gravitational upgrade of Heisenberg's principle has inspired decades of theoretical research. In string theory, for example, it appears naturally without being put in by hand. Strings, the fundamental one-dimensional filaments that replace point particles, resist compression inherently. The more energy you pump into them, the more they stretch and vibrate, spreading out spatially, instead of shrinking to points. Once again, nature protects its smallest domain from collapse through its fundamental structure. Even in loop quantum gravity, a theory that quantizes space itself into discrete units, a similar result emerges naturally. Distances and areas come in discrete units, indivisible quanta, each roughly the size of the Planck length. Below that scale, Geometry simply doesn't exist as we understand it. It's not there to be measured. You might think this all sounds purely theoretical, far beyond anything measurable or relevant. But its fingerprints actually appear subtly in black hole physics, which we can observe. When Stephen Hawking derived the radiation emitted by black holes through quantum effects near the event horizon, he found that their temperature and entropy depend on surface area measured in Planck units. That deep link between information, gravity, and quantum uncertainty may be a clue that the GUP is not just mathematical elegance, but physical to reality. It also fundamentally changes how we think about information itself. If there is a smallest possible length in nature, then there is also a smallest unit of information, a quantum bit tied to that scale. Every black hole, every region of space, carries a finite number of bits proportional to its surface area in Planck units. As physicist Jacob Bekenstein put it with great insight, the universe stores information not in its volume, but on its boundary, on surfaces. This simple but profound statement connects black holes, holography, and quantum uncertainty, three of the deepest threads in modern physics, all converging on the same fundamental idea. There is a natural limit to knowledge, not because we lack tools or imagination, but because reality itself is built that way. To illustrate just how strange this fundamental limit truly is, consider a thought experiment. Suppose you try to measure the position of a particle with extreme, ever-increasing precision. You use higher energy light, shorter wavelengths, and better detectors. Initially, your accuracy improves steadily as expected. But beyond a critical point, as you raise the energy further, the gravitational field of your measuring photon actually bends the particle's path, introducing new, uncontrollable uncertainty. Eventually, if you go far enough, you'd create a gravitational horizon around your own experiment. It's as if the act of asking where in space creates a ripple so strong that space refuses to answer the question. NASA and ESA's work in observational cosmology echoes this idea on vastly larger scales. When the James Webb Space Telescope looks at distant galaxies, it's also probing space-time structure, observing how light stretches as the universe expands. On the opposite end of scale, theoretical physicists do something remarkably similar with thought experiments, stretching the laws of measurement to their absolute breaking point. Both kinds of exploration, the cosmic and the quantum, meet at the same fundamental question: is there a smallest pixel of space itself? The generalized uncertainty principle suggests, yes, there is, but not as a hard wall you hit suddenly. It's more like a horizon of fuzziness, where the clarity of position and momentum trade places, blending into each other gradually. At that edge, the universe is neither continuous nor discrete, neither smooth nor rough. It's something in between, something our current mathematical language struggles to capture fully. Heisenberg himself could never have guessed that his uncertainty principle, discovered studying electrons in atoms, would one day touch the physics of black holes and the structure of space-time. Yet here we are, tracing the same quantum uncertainty he discovered in simple atomic systems all the way to the very structure of space-time itself. As physicist Lee Smolin once said, the quantum is not a theory of things in space, it's a theory of relationships between events. And when gravity joins that network of relationships, uncertainty becomes more than just a measurement blur, it becomes the architecture of reality itself. But if there's a smallest measurable distance encoded in nature, then what about the very substance of what we're measuring? If matter is made of waves, and space itself may be quantized, could the building blocks of reality be something more than point particles? If particles aren't dimensionless points at all, but tiny vibrating strings, does the idea of infinite sharpness still mean anything? That's the fundamental question that gave birth to one of the boldest theories in modern physics, string theory. By the late 20th century, scientists had already reached the limits of their existing equations. Quantum mechanics ruled the small scales beautifully. General relativity ruled the large scales elegantly. But between them, at the Planck length, both theories began to break down catastrophically. Every attempt to merge them into a unified theory led to infinities, impossible numbers that said quite literally the universe couldn't exist the way our mathematics described it. The problem wasn't in our telescopes or colliders, it was in our fundamental picture of matter itself. In all of physics up to that point, elementary particles were treated as points, zero-dimensional dots with no size, no spatial extent, just position and charge and other quantum numbers. That simplification worked beautifully for almost all of physics. But at ultra-high energies, the scales approaching the Planck length, it caused an absolute crisis. Because when two point-like particles collide in quantum field theory, all their energy focuses into an infinitesimal point. The mathematics explodes with infinities. Gravity becomes infinite. The predictions become meaningless. So what if, physicists wondered, the fundamental objects weren't points at all but strings? One-dimensional filaments, incredibly small, about the size of the Planck length, approximately 10 to the negative 35 meters. If particles were actually vibrating loops instead of dots, the infinities might vanish naturally. The energy would be spread along the string's length, never collapsing into a singular point. And remarkably, it worked. When theorists replaced point particles with strings in their equations, the infinities that had plagued quantum gravity disappeared like magic. Gravity, instead of breaking the equations, emerged from them naturally as an inevitable consequence. That was the revelation. In string theory, gravity isn't added to the theory by hand. It's a built-in, unavoidable consequence of how strings move and interact. At ordinary energies, the energies we can access in laboratories today, strings behave exactly like point particles. Their vibrations are so incredibly small that they appear point-like to us, indistinguishable from what we've always observed. But as you pump in more energy, as you metaphorically zoom in closer, the picture changes fundamentally. Instead of becoming sharper and more defined, the strings begin to vibrate more violently, sprouting new modes of motion. Their effective size actually expands rather than contracting. It's a perfect echo of what we saw with gravity and the generalized uncertainty principle. When you try to measure too precisely, the very act of adding energy blurs the picture. String theory takes that blurring and builds it into the foundation of matter itself from the beginning. At extremely high energies, far beyond any collider we can possibly build, a string can't be squeezed smaller than its own characteristic length. The more energy you add, the more it stretches and vibrates faster, vibrating into higher and higher excited modes. Like a guitar string tightening under tension, the resolution stops improving. Nature simply refuses to let you see finer detail. This leads to a remarkable conclusion. There is a minimum measurable distance in string theory, roughly equal to the string's own length itself, close to the Planck scale. Below that scale, the word distance loses operational meaning, not because space ends or becomes pathological, but because the tools we use to define space stop working in any meaningful way. The story of how this idea unfolded is as human as it is scientific. String theory didn't begin as a theory of everything. It began in the late 1960s as a model to explain the strong nuclear force, the force that binds quarks inside protons. Physicists working on particle collisions saw that the patterns of energy and angular momentum they measured could be described mathematically by the vibrations of a tiny string. But soon, something completely unexpected appeared in the mathematics. Uninvited, a vibration mode that behaved exactly like a graviton, the hypothetical quantum particle of gravity. That single detail changed everything. Suddenly, string theory wasn't just about the strong force, it was about all forces. It could potentially include electromagnetism, the weak and strong nuclear forces, and gravity itself, all woven together by the geometry of vibrating strings. Each vibration of the string corresponds to a different particle, much like the notes of a violin correspond to different musical sounds. The electron, the photon, the quarks, the Higgs boson, all could potentially be different harmonics of one underlying structure, different vibrational modes. As physicist Brian Greene beautifully put it, the universe is a symphony of vibrating strings, and the laws of physics are the melodies they play. The idea may sound poetic, almost too beautiful, but its implications are rigorously mathematical and testable in principle. String theory requires extra dimensions beyond the familiar 3 of space and 1 of time. Not just 4-dimensional spacetime, but up to 10 or even 11 dimensions total, depending on the specific version of the theory. These hidden dimensions aren't large like the ones we experience. They're curled up so tightly at every point in space that we can't detect them directly. These hidden dimensions determine how the strings can vibrate, and therefore what kinds of particles exist in our observable universe. The shapes of those hidden dimensions are called Calabi-Yau manifolds, intricate geometric structures that fold and twist in ways far beyond human intuition or visualization. Each possible shape corresponds to a different version of physics, a different universe with its own laws. Theorists estimate there could be 10 to the 500th power of such possible shapes, a number so astronomically large it defies comprehension. At this point, string theory becomes more than just a fix for infinities. It becomes a vast landscape of possible realities, a multiverse of possibilities. And yet, at its heart, it still answers a simple, profound question we started with. Why can't we zoom in forever? Because in a world fundamentally made of strings, infinite sharpness is an illusion. The string's own length defines the smallest possible scale. Beyond that, new energy doesn't reveal new detail or finer structure. It simply excites new vibrations, new resonances, new notes in the cosmic symphony. The picture doesn't sharpen, it sings. This built-in softness, this fundamental fuzziness, is what saves the fabric of reality from tearing itself apart at high energies. In point particle theories, collisions at infinite energy lead to infinities in curvature, singularities where mathematics fails. In string theory, those singularities are smoothed away naturally by the finite size of strings. The energy never concentrates into a mathematical point, so space-time never collapses. And from that smoothing, from that finite extent, gravity itself emerges naturally and inevitably. When strings interact and vibrate, one particular mode behaves exactly like the gravitational field described by Einstein. It's not an extra ingredient added to the theory. It's an inevitable outcome of the mathematics. That's why physicists often say that in string theory, Einstein's gravity simply falls out of the mathematics naturally. The universe doesn't need gravity added to it artificially. It's already there, encoded in the motion of every string. This insight brings a rare harmony to theoretical physics. For the first time, quantum mechanics and gravity can coexist peacefully, not as rival frameworks fighting for supremacy, but as aspects of the same underlying geometric structure. Space, time, energy, and vibration all become one unified language. Of course, we have yet to test this directly through experiment. The energies required to observe individual strings, on the order of the Planck scale, are far beyond any human experiment for the foreseeable future. But indirect evidence may one day appear, subtle patterns in the early cosmic microwave background, ripples in space-time from the early universe captured by gravitational wave detectors, or exotic particles predicted by supersymmetry might offer glimpses of this hidden structure. Until then, string theory remains a masterpiece of unification, a theory not yet experimentally proven, but astonishingly mathematically consistent. It gives us a framework where the smallest scale is not chaos or singularity, but music and harmony, where the deepest layer of the universe is not a wall blocking further progress, but a rhythm, a vibration. As theoretical physicist Edward Witten once said, string theory is not just a theory of strings, it's a framework that contains gravity and quantum mechanics, as part of a larger unified whole. And that larger whole may finally explain why space-time does not tear when we probe too deep, why nature's smallest details shimmer with quantum uncertainty instead of shattering into singularities. But there's another possibility, one even stranger than strings vibrating in 10-dimensional space. What if space itself is not continuous at all, but fundamentally made of discrete quantum building blocks? Tiny, indivisible chunks of area and volume woven together by the quantum spin of space-time itself? What if the smooth fabric of space-time, the one Einstein described so beautifully and convincingly, isn't smooth at all underneath? What if beneath everything we know and observe, the universe is actually woven from discrete quantum threads, a cosmic lattice, granular and finite, rather than infinitely divisible? That is the daring question behind one of the most fascinating theories in modern physics, loop quantum gravity. It begins not with strings or vibrations of energy, but with geometry itself, with the structure of space. Where string theory treats the universe as a symphony of energy in vibrating strings, loop quantum gravity treats it as a network of quanta of space itself, a fabric woven from geometry. To understand why this radical idea matters so much, we have to revisit a fundamental problem Einstein left unsolved. His general theory of relativity tells us that gravity isn't a force pulling at a distance through space. It's the curvature of space-time caused by mass and energy. Planets move along curved geodesics in this geometry, and light bends following those curves. Everything flows smoothly in that elegant geometric framework. But when you zoom down to the smallest scales, to the Planck length scale, that smoothness begins to crumble and break. Quantum fluctuations shake space-time like ripples on a restless sea. The continuous surface Einstein described so perfectly no longer holds together. Loop quantum gravity takes that breakdown seriously, embracing it. It doesn't try to unify gravity by adding new particles or postulating extra dimensions. Instead, it rewrites the very idea of what space is at its foundation. According to loop quantum gravity, space is not continuous at all. It's quantized into discrete units. Just as light comes in discrete packets called photons and energy comes in quanta, space itself comes in tiny, indivisible units, the smallest possible chunks of area and volume that can exist. These are unimaginably small, each roughly the size of the Planck scale. In this picture, the geometry of space-time is made of a vast network called a spin network. Each node of the network represents a quantum of volume, a tiny piece of space. Each link between nodes represents a quantum of area, a tiny surface. Together, these form the microscopic scaffolding of the universe, the hidden architecture beneath the smooth appearance. When viewed from afar, at human scales and even atomic scales, this network looks perfectly smooth, just as a beach looks smooth from a distance, even though it's made of countless individual grains of sand. But up close, at the Planck scale, the continuity dissolves into discrete, vibrating units. It's a radical but mathematically elegant idea. Space is built from quantum loops, closed loops of gravitational field lines woven together, forming a fabric of finite, interconnected regions. Time, too, is quantized in this framework, progressing in tiny jumps instead of flowing continuously. Reality, at its deepest level, ticks like a quantum clock rather than flowing smoothly. Carlo Rovelli, one of the founders of loop quantum gravity, explains it simply and powerfully. At the Planck scale, space is not continuous. It is made of grains, discrete units. The world is woven from loops of gravity in quantum form. Working out the mathematics, physicists found that areas and volumes can only take on discrete, quantized values. Much like how the energy levels of an electron in an atom are quantized and cannot be arbitrary, you can't have a fraction of a quantum of volume. That means even empty space, even the vacuum, is made of structure, a quiet web of quantum geometry that sets the stage for everything that exists. Space is not nothing. It is something with its own atomic texture at the smallest scales. At larger scales, this discrete texture averages out, giving rise to the smooth spacetime of general relativity that we observe and measure. So remarkably, Einstein's theory isn't thrown away or contradicted. It's recovered naturally from the quantum behavior of these loops when you zoom out to larger scales. In the language of physicists, general relativity emerges as the low-energy limit of loop quantum gravity. In other words, space-time smoothness is an illusion born of scale, like mist that when magnified reveals countless individual droplets. To see how truly revolutionary this framework is, consider what it means for singularities, those points of infinite density predicted at the centers of black holes or at the Big Bang itself. In classical general relativity, those singularities mark the points where equations break down completely, where physics ends. But in loop quantum gravity, the quantum structure of space naturally prevents such infinities from forming. Space cannot compress beyond one. Quantum of volume, 1 Planck unit. That means, in principle, the Big Bang was not a beginning from nothing, not a true singularity, but a bounce, a transition from a prior collapsing universe that reached minimum size and then re-expanded. This idea is sometimes called the Big Bounce, and it arises naturally from loop quantum gravity's equations. NASA's WMAP and ESA's Planck satellites have observed the oldest light in the universe, the cosmic microwave background, giving us a remarkably detailed picture of the universe, as it was about 380,000 years after the Big Bang. These observations match beautifully with the predictions of general relativity and standard cosmology, but they can't yet see what happened before that time, during the earliest moments. Loop quantum gravity suggests that before still existed, just governed by quantum geometry rather than classical spacetime. If this is true, then every atom, every planet, and every galaxy is suspended in a vast network of quantum threads at the smallest scales. The strength of gravity, the passage of time, even the shape of space, all emerge from the way these fundamental loops twist and connect. It's an idea that's as strange as it is logically compelling. After all, we already know that energy and matter are quantized. Why should space itself be fundamentally different? Experimental confirmation, however, remains frustratingly elusive. The Planck scale is far beyond our current reach. No telescope or accelerator can probe it directly. But physicists are searching persistently for indirect clues. Tiny imprints in the polarization of cosmic light, or subtle irregularities in the timing of gamma-ray bursts that travel across billions of light-years. If spacetime really has a granular structure at small scales, photons of different energies might travel ever so slightly differently, a faint fingerprint of the underlying lattice. Such signals would be extraordinarily faint, but the tools are steadily improving. NASA's Fermi Gamma-Ray Space Telescope and ESA's Integral mission are scanning the skies for precisely these patterns. So far, spacetime appears smooth within measurement precision, but the search continues with increasing sensitivity. Loop quantum gravity stands as a kind of quiet counterpoint to string theory. It doesn't need extra dimensions beyond the four we experience, or exotic new particles. It takes the geometry of space, Einstein's great legacy, and quantizes it directly. Where strings sing their harmonies, loops weave their patterns, and both in their own distinct ways whisper the same fundamental truth. At the Planck scale, there is no such thing as empty space. There is only structure, humming silently beneath the surface of reality. This perspective transforms how we imagine the universe at its deepest level. The cosmos is not a smooth stage where matter performs its dance. It's a living network, dynamic and self-interacting. Matter curves space through gravity. Space tells matter how to move through curvature. And beneath both lies a hidden architecture of loops and links, of quantum geometry. And as strange as it sounds, this quantum geometry could be the key to finally uniting the two greatest theories in physics, quantum mechanics, and relativity, without fundamental contradiction. a universe built not from particles existing in space, but from space itself becoming quantum at the smallest scales. As physicist Lee Smolin once wrote eloquently, space is not what it appears to be. It's a network of relationships between quanta, a web that gives rise to smooth geometry when viewed from afar. So what happens if we attempt to go even deeper, beneath the loops, beneath the geometry, to where information itself might be the fundamental fabric of reality? What if space-time isn't just quantized, but emergent, a byproduct of something even more basic and abstract? What if the very thing we use constantly to describe reality, distance itself, is no longer real at the deepest level? What if near and far, before and after, here and there, are only useful approximations that dissolve when we look too closely? That question marks the quiet edge of modern physics, the boundary where our most basic concepts begin to fail. Because after centuries of measurement, calculation, and observation, from Galileo's first telescopes to the James Webb Space Telescope, we are finally reaching a limit not set by technology, but by nature itself, by the structure of reality. It began with two separate paths, two independent lines of reasoning that astonishingly both point to the same profound conclusion. One comes from the gravitational collapse of energy, the other from the quantum limits of measurement. The first path is purely relativistic. Einstein's theory tells us that energy curves space-time. When too much energy is concentrated into a small region, the curvature grows so steep that light cannot escape. A horizon forms. The region becomes a black hole. This means that if you try to probe distances smaller and smaller by using higher and higher energies, you eventually cross a threshold where your own experiment collapses into a gravitational well. Beyond that point, nothing, not even information, can return. The act of measuring destroys the very thing being measured. The second path comes from quantum mechanics. Heisenberg's uncertainty principle tells us that every measurement has a built-in fuzziness. The more precisely we try to measure position, the less precisely we can know momentum. This is not a flaw of our instruments. It is a property of the universe. But when we add gravity to that principle, when the measuring photon itself has energy that bends space-time, something remarkable happens. Increasing energy to sharpen position eventually increases curvature, which blurs it again. There's a balance point where further precision is impossible. This modified rule, the generalized uncertainty principle, tells us that below the Planck length, about 1.616 times 10 to the negative 35 meters, the concept of distance ceases to make physical sense. It is not that we lack the right microscope, it's that the universe itself no longer offers coordinates to define closer or farther. Two different lines of reasoning, one from gravity, one from quantum theory, lead to the same boundary, the Planck scale. At that boundary, Einstein's smooth space-time and the probabilistic world of quantum mechanics are no longer separate languages. They merge, clash, and demand a new grammar, a unified theory that treats both as equals. That quest to unify gravity and quantum mechanics is the central story of modern theoretical physics. Two great paths have emerged: string theory and loop quantum gravity. String theory proposes that everything from electrons to space-time itself is made of tiny vibrating filaments of energy. These strings are incredibly small, roughly the size of the Planck length. They don't allow infinite sharpness. When you add energy, they stretch and oscillate, never collapsing into a point. Gravity arises naturally from their motion. Loop quantum gravity takes a different approach. It starts not with strings, but with space itself. It treats geometry as quantized, built from discrete loops and nodes called spin networks. Volumes and areas are not continuous, but granular. Each one, a quantum of geometry, roughly the size of the Planck scale. Both theories, though distinct, point toward the same profound conclusion: space and time are not fundamental. They are emergent byproducts of deeper relationships. The smooth space-time we see is like a mirage. that appears when countless quantum interactions blend together. At macroscopic scales, galaxies, planets, oceans, and atoms, this mirage works perfectly. GPS satellites depend on it. Light follows it. NASA's spacecraft navigate through it with astonishing accuracy. But zoom far enough down, and the coordinates that guide rockets and stow photons begin to dissolve. At the Planck scale, a ruler has no meaning and time, no sequence. The universe is not here or there, but a web of interactions flickering between potential states. It's a strange place to imagine, yet it might be the birthplace of everything we see. The laws that shaped the first instant after the Big Bang, the inflation of space, the formation of matter, the seeds of galaxies, all trace back to this regime where geometry itself was quantum. NASA's WMAP, ESA's Planck, and now JWST have pushed our observational limits ever closer to that beginning. They can see the universe as it was hundreds of millions of years after the Big Bang, when the first galaxies lit up the darkness. But the true origin, the quantum moment of spacetime's birth, remains hidden behind this natural wall of uncertainty. Carl Sagan once said beautifully, "We are a way for the cosmos to know itself." But now it seems the cosmos has drawn a boundary around its own reflection. We can observe the stars and galaxies. We can trace the curvature of space-time, but beyond a certain precision, nature refuses to be seen. It's not a dead end, it's an invitation. Because if distance itself is only an approximation, then physics must find a language deeper than geometry. A theory not of where things are, but of how things relate. In some versions of quantum gravity, that's exactly what happens. Space emerges from entanglement, from the way quantum information is shared between systems. The very act of connection creates geometry. In that view, distance is not a property of the universe. It's an effect of interaction. Space exists because particles exchange information. Without interaction, there is no between. It's a breathtaking thought. At the deepest level, reality may not be made of things, but of relationships. The universe, then, is not a place, but a process. As you reflect on this long journey we've taken together this evening, from the visible world down to the Planck scale, remember that every step revealed not just smaller structures, but deeper principles. We've seen how light fails where electrons succeed, how protons hide quarks, how the universe itself pushes back against our attempts to see too deeply. We've encountered string theory's vibrating filaments and loop quantum gravity's quantum foam, two different paths to the same destination. And we've learned that distance itself, the very notion of here and there, is only an approximation that breaks down at the smallest scales. This is where we find ourselves now, in the early 21st century, standing at the edge of knowledge, peering into darkness beyond, knowing that something profound awaits, but not yet able to see it clearly. This is the nature of science. Always reaching, always pushing further, always seeking deeper understanding. The Planck scale is not a wall that stops us, it's a horizon that calls us forward. Beyond it lies either the end of physics as we know it, or the beginning of physics as it will be. Either way, the journey continues, and the adventure of understanding never ends. Thank you for joining me on this deep exploration into the fundamental limits of reality. If this quiet journey has brought you even a moment of wonder, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe means more than you might think. It's a quiet sign that these explorations matter to you. And if you'd like, please share in the comments where in the world you're listening from tonight. Your words, your presence, are like small lights scattered across this dark and endless cosmic night. Thank you for exploring with me. Until next time, rest well, and may your dreams drift gently among the stars.